So one thing you want to keep in mind, remember the moment of inertia for a point mass is mr squared, where the m is the mass of the point mass, and r is the distance from the axis that it's rotating about. A point mass is literally just a mass whose dimensions are so small you can neglect them, right? So you're not dealing with a sphere that has an actual moment of inertia or a disk or anything like that. It's a point mass that has such small dimensions that they're negligible. If you have, say, a collection of point masses, so this is a pretty common problem. Say I have a collection of point masses, and they are rotated about this point, and they're on a rod of negligible mass. Well, an object with negligible mass has zero rotational inertia. So the total rotational inertia of this system of objects would be the rotational inertia of this guy plus the rotational inertia of that guy, where the masses might be the same, but the R values will obviously be different. Okay. So when you have a compound object like this, the total rotational inertia is just the sum. And I like to point out it's because of this. When we talk about the rotational inertia of this rod, which is 112 ml squared, I pointed out before, the way that we do this, and you'll learn this from Miss Fudge when you take calculus, is we take this rod, we divide it up into an infinite number of infinitesimally small masses, and each one of those little tiny pieces of mass is considered to be a point mass, each with a tiny, tiny, infinitesimally small amount of mass m, but each little tiny m is going to have a distance r from the axis of rotation, right? And then I literally add up all those moments of inertia for all of those little tiny pieces of mass, and that's where this equation comes from, where the m here is the total mass of the object, and the L is the total length, okay? So the reason I point that out is because if I do have a compound object with multiple objects located on it, then the rotational inertia is literally just the sum. Okay, but you just got to be careful about the R values and the individual M's. Make sense? Okay. So I think number 2 has you determine the rotational inertia of a diatomic nitrogen molecule, where you have 2 nitrogen atoms connected by the bond length, right? About that center of mass, the nitrogen atoms are point masses, and you just divide the bond length by 2, right? And that's going to be the R value for each point mass, and then you just double it because you got 2 of them, so you got to add them together. Yes, you do consider them to be point masses. You don't worry about the dimensions of the actual atoms. And in fact, when you deal with ideal gases, which you guys know all about, ideal gas is one of the assumptions that goes into whether a gas is behaving ideally or not, is you neglect the actual mass, you neglect the dimensions of the gas molecules. They're so small that they're inconsequential, and that's a fine assumption most of the time. Okay. One of the trickier problems involves a setup like this, where I have a rod rotated about its end that's initially horizontal, and then it's released, and it accelerates down. It just swings down. Okay. Understand that here we can figure out the initial angular acceleration by using Newton's second law for torques. The problem with algebra-based approach to this is that as soon as it starts rotating, the angle between the lever arm and the weight force is changing, right? And it actually constantly changes as the rod swings down. And so those of you that know calculus or that will learn calculus eventually, you'll learn that calculus is literally the mathematics of changing systems. And so because that variable theta changes as the object accelerates down, the angular acceleration will constantly be changing, and calculus is the mathematics that allows you to track those changes, right? With just algebra, all you can do is figure out the angular acceleration at a certain time, right, based on the angle that the lever arm makes with the weight force. And so that's what you're going to have to do for this particular problem. And you're also going to have to relate the angular acceleration that you can calculate to the tangential accelerations of several points on the rod. So we know this rod is going to have a certain angular acceleration. It's going to have a certain angular acceleration, and every point on the rod has that same angular acceleration, right? Because every point on that rod is going to be sweeping out the same angle per unit of time. But each one is going to have a different tangential acceleration, and as you probably can conceptualize, the farther away you get, the faster the points on the rod are going to have to be accelerating tangentially, right? And so this one would have the highest. And how I figure those out? Well, first I figure out the angular acceleration by doing the net torque, doing Newton's second law for torques. Well, I only have one torque here. It's the weight force of the rod. The torque due to the weight force. So you have force times the lever arm. Well, this R right here would be L over 2. We always draw, if this is a uniform rod, we draw the weight force from the center of mass. So the distance from the end to the center of mass is L over 2. Rotational inertia of the rod, you don't have to memorize this, but a rod rotated about its end is 1/3 ml squared. So that's my rotational inertia, 1/3 ml squared, times the angular acceleration, right? So we can determine the angular acceleration using Newton's second law for torques. And then once we have that, we can relate the tangential acceleration at different points on the rod to that using that equation. Okay. So if I want to know the tangential acceleration at point A, then I have to say, all right, I find the angular acceleration that is the same for all 3 points, multiply it by the distance from the axis of rotation to that point A, and obviously it's going to be making a circle, but initially it's going to have that tangential acceleration. Same thing for point B, right? Now, that distance to point B is going to be larger, and so with the same angular acceleration, I get a larger tangential acceleration. The end result, the problem that I'm dealing with, and I'm going to set this up for next week, you have a meter stick that's set up like this, and coins are placed on different points on the meter stick, and then the meter stick is released, and you're tasked with figuring out which one will actually break contact with the meter stick as the meter stick goes down. You probably will expect that the ones closer don't. The ones farther, more likely to actually come up off the meter stick as it accelerates downward. And the way that you are going to handle that is by determining the tangential accelerations of each coin, of each point on the rod on which the coin is placed. And then you got to make a comparison there that I'm going to let you use your noggins to figure out. Okay. That's it. Minimum day. That's it for today. So, yeah. Goodbye.